So I'm truly delighted to be able to introduce Steve Weinberg, one of my teachers and mentors from whom I've learned so much. But I'm also delighted because this gives me an opportunity to say a few words about Joe Polchinski, because I first met Joe at a dinner party at Steve Weinberg's house in Austin, and was 31 years ago. So by simple arithmetic, Joe was still a youngster in his 20s. And now I remember that Steve had assembled quite a few smart people in his house that evening. But when I met Joe, I thought, wow, this guy is somebody we should maybe try to bring to Santa Barbara. And several years later, the opportunity did arise, and I was delighted that Joe came, and I was enjoyed 20-some years of being his colleague. A lot of people here have all said how smart he is, but he has another truly rare quality in our community, which is that he's an incredibly nice guy. And not only to other physicists, but to children and the children of other physicists and so on and so forth. But he just told me he had me fooled all these years. So I very much would like him to continue to fool us. So Steve, is now all yours.
Well, good morning. I'm awfully sorry that I can't be there with you in the flesh to say happy birthday to Joe and hello to you all. I'm grateful to the conference organizers for making this remote hookup possible. Although I feel I'm very friendly toward Joe, he did cause me considerable pain twice in my life. The most important occasion was when he let me know that he was leaving Austin to go to Santa Barbara. Tony, I'll never forgive you for that. And we had to close the cafe where Joe had done some of his best work, the Captain Quackenbush's Intergalactic Cafe and Dessert Bar. I think Joe probably remembers that place.
That's where the Google Plexus was written.
The other occasion was actually close to the subject of my talk today. Back in the late 1980s, I was thinking about the question whether there were any small corrections to quantum mechanics, whether we could do experimental tests to say, not to test any one quantum mechanical theory, but to test quantum mechanics itself. And my attention focused on the possibility that there were corrections to the linearity of the time-dependent Schrödinger equation. Can I have the first slide, please, if it's not already up? I set up a nonlinear generalization of quantum mechanics. This was not in order to resolve any of the classic profound questions that are raised by quantum mechanics, but just to see whether there was any way of testing it experimentally. And I found that experiments at the National Bureau of Standards had already set very stringent limits. Well, they could be interpreted as setting stringent limits on any nonlinearity. And then Joe came in and told me that you didn't need these experimental limits, that there was a theoretical limit, that any nonlinearity of the sort I was considering, at least, in quantum mechanics would allow for the instantaneous communication between distant systems as long as they're suitably entangled. And this is the kind of Einstein-Podolsky-Rosen effect, but actually leading to communication if you're not careful with the nonlinearities. In fact, Joe even showed that you could get communication between different worlds in what is usually called the many worlds description of quantum mechanics. Really spooky. The problem of communication between, instantaneous communication between distant, separated subsystems was put in a nice summary by Jezin, who proved a neat little theorem that said if you have two isolated systems and you fix the density matrix of the first, then you can always entangle them in such a way that measurements in the second will put the first system in any ensemble of states you like with any probabilities, as long as you preserve the density matrix. You can make any change you like in entangled systems that are isolated, however far apart they are, as long as you don't change the density matrix. Now, this is okay in ordinary quantum mechanics because from the density matrix you can infer everything that you could measure, and also the density matrix in ordinary quantum mechanics obeys a differential equation. We're now in the second slide, please. It obeys a differential equation which just depends on the density matrix, so it doesn't really matter what the state vectors and probabilities are. But still, if state vectors can be changed instantaneously by distant measurements, you wonder whether you should be taking them seriously as a representation of reality. And also, on a more practical level, if you try to introduce nonlinearities, as I recently did, into quantum mechanics, reintroduce them as a way of improving on the Copenhagen interpretation of measurement, then again the problem that was pointed out to me by Joe rears its head, and you wind up with instantaneous communication between distant systems. Thinking about this has led me to make a modest proposal. Next slide, please. The proposal is that we should forget about states, state vectors, and that a statement that a system is in an ensemble of state vectors with various probabilities simply has no physical significance except for what it tells you about the density matrix. The same density matrix will describe many different ensembles of states and probabilities, but only the density matrix has physical significance, and you can forget about the states and the probabilities. To take an example, and next slide, please. I hope we're on the slide that on top says example, spin a half. I can't see the slides as you're showing them. We should be on slide 4. If you take a spin a half particle and forget everything but its spin, you could describe it, for example, as being in pointing north, south, or east with various probabilities, 50%, 15%, 35%. Or you could say it points northeast with a probability of 75% and southwest with a probability of 25%. These sound very different, but in fact they're indistinguishable. And they better be indistinguishable because, as Jezin showed, you can always arrange an entanglement with some distant system that's isolated from the spin-a-half particle and instantaneously change from the first description to the second description. In fact, could you go to the next slide, please? What I've done here is to take those descriptions in terms of states and probabilities and convert the color to yellow so that you can't read them, and put at the bottom the only thing that, from the point of view I'm selling, is physically significant, the density matrix, and there it is. Now, if you're giving up the idea of physical states as fundamental, then what is the density matrix? We usually define it in terms of an ensemble of pure states with definite probabilities. Well, like everything else, it can be defined in terms of what we do with it. One can take as an interpretive postulate that the mean value of any observable that's represented by an operator A is the trace of the density matrix times A. We should be on a slide now that slide number 6 that says interpretive postulate in red. With this as the definition of the density matrix, all the properties of the density matrix that usually are derived from its representation in terms of physical states follow immediately. The density matrix has to be Hermitian in order that the mean value of an operator of an observable represented by a Hermitian operator be real. The density matrix has to have unit trace in order that the mean value of the C number equals that C number, and the density matrix has to be positive in order that the mean value of an observable represented by a positive operator be positive, like the square of a Hermitian operator. Well, you don't need any new philosophy to just to express an interest or an emphasis on the density matrix. If you pick up any book, for example, on quantum information theory, you find it's just filled with the density matrix. Everyone has known for many decades that the density matrix is a good thing. So what's the difference in what I'm proposing? Well, one big difference is that once you give up the idea that the density matrix is defined in terms of an ensemble of physical states with definite probabilities, you're free of the Wigner theorem. The Wigner theorem says that the phases of physical states can be chosen so that any symmetry operator acting on them acts as a unitary operator, unless it involves time reversal, in which case it's an anti-unitary operator, but forget that. So, in other words, if the density matrix is defined as usual in terms of physical states with definite probabilities, then under any symmetry transformation, it undergoes. Oh, I'm sorry. You should be now on a slide that says, what's the difference?
Don't worry, we're following.
It's slide number 7.
Don't worry.
And on top in red, it says, what's the difference? Then in the conventional definition of the density matrix, it has to transform unitarily. Rho goes to U, rho, U adjoint. But if you don't insist on that understanding of the density matrix, but just take it as a thing from which you can derive mean values, then the density matrix could be transformed by any kind of linear transformation, characterized by a D square, where D is the dimensionality of the Hilbert space, a D square dimensional kernel K. This is not entirely new. This has already been considered widely for the case of time translation, partly originating in the theory of open systems, where you integrate out the environment and you get a equation for the density matrix for the time dependence of the density matrix, or in other words, for its transformation under time translation, which involves a mapping like the one I described in terms of this kernel K. And this goes back to the 1970s, various authors, and it's been used as a basis for extensions of quantum mechanics to try to deal with the measurement problem by a well-known paper by Girardi, Rimini, and Weber, and other papers by Pearl, and so on. In these latter papers, they go to great efforts to show that the kind of evolution of the density matrix that they're considering is one that can be realized by a stochastic linear evolution of state vectors. From the point of view I'm offering today, that's unnecessary. The important thing is only the evolution of the density matrix. Forget state vectors. To take an example where the density matrix could transform in a way that couldn't possibly be realized by the kind of unitary transformation you have in ordinary quantum mechanics. Take a three-dimensional example. You can imagine that where the density matrix is a 3 by 3 matrix, you could imagine the elements above the main diagonal transforming as a 3, with a symmetry SU3. Oh, I'm sorry, we should now be on the next slide, which says an example. You can imagine that the density matrix elements above the main diagonal transform as a 3. The density matrix elements below the main diagonal transform as 3 bar, which is necessary so that the density matrix be Hermitian. And the ones on the main diagonal be invariant, be singlets. This transformation is impossible in ordinary quantum mechanics because there the density matrix, the unitary transformation of the density matrix would force it to transform as an octet plus a singlet, which is not consistent with 3 plus 3 bar plus 3 singlets. So I just wanted to show you right away that giving up the description in terms of state vectors does widen the possibilities of symmetry operations on the density matrix. Now, to go beyond that sort of trivial example, one can consider general symmetries. Could you go to the next slide, please? It's one that says on top in red, general symmetries. In my numbering, it's number 9. The density matrix, as I said before, is just transformed by the most general linear transformation you can imagine. If you impose the condition the density matrix has to be Hermitian and remain Hermitian when you make any kind of symmetry transformation, then you find that this kernel K satisfies a kind of hermiticity property. The indices on K are written in a peculiar-looking order. I don't write it as M prime, N prime, comma, Mn, which is what you might think, but the reason for writing them in this order is then if you think of K as a d squared by d squared dimensional matrix, it is an ordinary Hermitian matrix. The fact that for a density matrix with a definite trace like unity, the trace is not changed by symmetry transformations, that gives you a sum rule for the density matrix. And by the way, the right-hand side here is wrong. It's just miscopied. It should be delta Mn, not delta N prime N, which is nonsense. Finally, those are easy. The condition that the density matrix, the transformed density matrix, should be positive for a positive row, we don't know a necessary and sufficient condition for that. That is a difficult question which I'll have to return at the end of my talk, but I have a lot of grief with that question. Now, I won't spend it. Could you go to the next slide, please? It says transformation of entangled systems. I won't spend any time on this slide. I just want to say that you can show, as shown here, that even in an entangled system, if you have two isolated parts of the system, which are characterized by a factorization of the kernel describing symmetry transformations, that because of the way the density matrix operates, the transformation of the part of the density matrix referring to one subsystem is unaffected by the nature of the other subsystem, and in particular is unaffected by what the transformation does to the other subsystem. In the special case where we're talking about time translation, that's the old result, that as long as you stick to the density matrix, nothing can be changed instantaneously by operations on remote subsystems. Now, there is a very useful representation of the kernel that defines these mappings in terms of its eigenvectors. Since it's Hermitian matrix, it's a Hermitian d-square dimensional matrix, it can be expanded in terms of eigenmatrices, which you can think of as d-square dimensional vectors. And I'm sorry, I'm now on a slide, the next slide that says because k star equals something, slide number 11, k then has a representation in terms of these eigenmatrices, and the trace condition can be expressed in terms of them. The transformation of the density matrix can be written in a very pretty index-free form. Rho prime is this sum that I give below. And if you have several of these eigenvalues of the kernel that are non-zero, this is a non-trivial generalization of the transformation of ordinary quantum mechanics. In the case where there's only one non-zero eigenvalue, this is ordinary quantum mechanics. There, the trace condition is the condition that U is unitary, and the formula for rho prime is just what you would expect if you do ordinary quantum mechanics. Actually, only provided that that eta would have to be positive in order to satisfy the trace condition, and then you can absorb the square root of eta into the U's, so that you have an ordinary unitary transformation. So far, I haven't done anything that isn't already familiar to the people who have worked on time translation, that is, the time dependence of the density matrix in generalized versions of quantum mechanics, like that of Girardi, Rimini, and Weber. The new thing, but if you're going to do this for time translation, you ought to be willing to do it for general symmetry groups. And there you have to confront something which the people like Girardi, Rimini, and Weber didn't have to confront, the group multiplication law. We have to require that the product of two group transformations is the kernel that corresponding to the product of the group elements. And this is a strong constraint. We should be now on the slide that says group multiplication law. That's the worst thing about giving this talk remotely. I can't see the slides.
We're with you.
There's a long analysis here of the application of this to continuous symmetries. This is on slide 13, which has continuous symmetries at the top. The next slide has trace condition at the top, and then the use of the group multiplication law. It winds up with a slide in which there's a single very long equation. This is slide number 16. In ordinary quantum mechanics, we learn a good deal about the structure of the Hamiltonian just from Galilean invariance. For instance, the form of the kinetic energy is essentially fixed by Galilean invariance. In the extended version of quantum mechanics that I'm describing here, instead of using the simple Lie algebra of, say, the Galilean group or any other symmetry group you're talking about, as a condition on, the commutators of those elements of the Lie algebra with the density matrix, instead of using that information, you have to use this very long equation here. And I don't know any general procedure for implementing it, but I did, in the case where, the next slide which says ordinary quantum mechanics describes how this in some cases reduces to ordinary quantum mechanics, but it doesn't in general. And the slide 13, which is headed a sample solution with these quantities which represent departures from quantum mechanics called capital delta not equal to 0, I give a sample solution which shows that it really can give you something quite different from ordinary quantum mechanics. I'm almost out of time, but I wanted to take up the question of positivity that I referred to earlier. We need that the density matrix should be, after a symmetry transformation, should be positive for all density matrices that you're transforming. And this is okay if the eigenvalues of the kernel, K, that represent symmetry transformations are all positive. In that case, it's trivial that the density matrix after the transformation will still be positive. But that isn't possible if you have a symmetry. That is to say, it isn't possible to have all the eigenvalues positive if you have an honest-to-God symmetry group. I give an example for continuous symmetries where it's fairly obvious, but that can be generalized in a theorem. And by the way, we should now be on a slide that says positivity on top. It's slide number 19. There is a theorem that if a symmetry transformation has an inverse, and if all the etas for the symmetry transformation and its inverse are positive, then the transformation of the density matrix reduces to just the one you have in ordinary quantum mechanics, and nothing new comes up. And the next three slides give the proof of this theorem. I wasn't even dreaming I could go into that in this talk, but it is, actually took some work to do, but it is a general theorem that applies to finite transformations as well as continuous transformations. Now, I should explain that for those authors who have already gone beyond ordinary quantum mechanics in the case of time translation, assume the condition that the eigenvalues are positive only prospectively, not retrospectively. That is, time translations that take you into the future have eigenvalues that are positive. If they take you into the past, the eigenvalues are negative. So if you start with a density matrix that is positive at some time, some initial time, then you are assured that the density matrix will be positive at all future times. But in fact, not at past times, and in general, it isn't positive at past times. There are various arguments that they give that show that argue anyway, that that's all right, which I won't go into. Under the assumption that you have, so in other words, they're dealing with a semi-group, not with a group. Under the assumption that you have transformations where the eigenvalues are only positive where you're going into the future, the condition that I showed on an earlier view graph, or on an earlier slide, we don't use view graphs anymore, for the time translation symmetry becomes what is known as the Lindblad Equation, which is the basis for all these studies of the evolution of the density matrix in extended versions of quantum mechanics. And I have a whole separate paper dealing with applications of the Lindblad Equation, which I don't have time to go into. But clearly, since the condition that the eigenvalues of the kernel all be positive is so powerful, and in particular, if you really take it seriously for a group, not just a semi-group, so that it applies to the inverses of transformations as well as the transformations themselves, then it implies that you don't get anything new in the way of transformation of the density matrix. You have to ask the question, and now we're on what should be slide 24, which starts out, do we need all etas to be positive in red? The answer is no, not necessarily. It's well known that you could have the transformed density matrix be positive even if some of the etas are negative. The classic example is the transposition map, where the eigenvalues are plus n minus 1, but the density matrix, the transformed density matrix is just the transpose of the density matrix, which is certainly positive as the density matrix is. there is an argument for all the eigenvalues to be positive, which goes back to a condition called complete positivity, which relies on inventing a kind of auxiliary subsystem which is isolated from the system you're looking at, and demanding that positive density matrices in the extended system, which contains this auxiliary subsystem, be positive even when the two subsystems are entangled. That, as shown in a theorem by D.M. Choi, shows that, that condition of complete positivity has the consequence that all the eigenvalues of the kernel have to be positive, and then you're back in ordinary quantum mechanics. There's no question that Choi's theorem is mathematically valid, but there is a question whether it's physically relevant, because Choi assumes certain things about the nature of this extended system, the way the auxiliary system is introduced, which may not be physically possible. I don't know the answer. If Choi's theorem is physically relevant, if it really does apply to what you have in the real world, then I think you can take what I've been talking about here today as a statement of a theorem that even if you're willing to consider the density matrix itself without relying on state vectors as the basis for quantum mechanics, you can't get away from the symmetry transformations of ordinary quantum mechanics. Alternatively, as I suspect, it may be that Choi's theorem is not physically relevant, that the kind of entanglement he's talking about is not physically realizable, in which case this is a real extension of quantum mechanics, which seems to me physically plausible and will require a great deal of work to see how to invent these kernels in such a way that, like the invention of the Hamiltonian in ordinary quantum mechanics, so that they represent physical reality. Well, thanks a lot, and I look forward to any comments or questions.
Well, I'm going to take the privilege to speak first and have a number of things to say. First of all, thank you, Steve, for your contribution, and I'm sorry you couldn't have made the trip. So I mentioned last night at dinner that you didn't have a 60th birthday celebration, and so you never got roasted, and this seemed to be a good time to make up for that. But in fact, everybody here has been very nice to me, and I'll also be nice to you. First, if it's any consolation, I still feel guilty about leaving Texas. Every day I'm riding my bike out in the beautiful weather, and I'm feeling very guilty. But my 8 years in Texas were a fantastic experience. I got to see firsthand your prediction of the cosmological constant. And this is just one of the many examples I saw of your approach to science, which is fantastic. It's your ability to, as in your talk today, to relax the assumptions that everyone else makes, and then to follow, not to be lazy and reintroduce them, but to follow that to its logical conclusion. I also started my book there. My goal was to make it as clear and easy to read as your book on gravitation, and I feel that I failed along many axes. Third, it was just a great place to develop as a scientist. I started my peculiar journey through string theory there, and I got to interact with some great students, several of whom are here today, and also great postdocs, several of whom are here today. now, coming closer to the subject.
Well, you all come back now. You hear?
Thank you. Coming back to the subject of your talk today, in this firewall story, people who are trying to avoid the firewall, it seems as though they are, in a number of different ways, relaxing quantum mechanics. There's this fellow here, Susskind, who believes that you can send messages in space-like directions using EPR correlations, provided the receiver is inside a black hole. Do you believe that?
Oh, I don't know. Black holes, to me, are black holes. I mean, in the sense of the black hole of Calcutta. I don't know.
But
I don't believe you can send messages in ordinary circumstances between distant, isolated systems instantaneously. And unfortunately, the kind of nonlinear generalization of quantum mechanics that I was studying a long time ago does allow that. So whatever happens in black holes, it killed off that line of speculation. I'm trying to offer an alternative route. But what happens when you communicate with someone inside a black hole? That's a fascinating idea, Lenny. I've never even dreamed of anything like that. But I have a suspicion that what I'm talking about today is not going to help with that.
So, I mean, there's some question maybe as to whether one is giving up space-time locality or quantum mechanics. But if there's this thing called state dependence, which really seems as though for different observers, there's a mapping between their density matrices, which is even more unconventional than what you described today, because it's actually genuinely nonlinear even in the density matrix.
Yeah, I should have said, if I had more time, that I was limiting myself only by the condition that the mapping of the density matrix be linear. And the reason I was doing that, because it was only in that context that I understood how to deal with isolated systems, how to define what you mean by one system being isolated from another. The definition is that the linear kernel for the operation of any symmetry operation factorizes between the two systems. Just like in ordinary quantum mechanics, if you have two isolated systems, e to the IHT factorizes because H is the sum of the H's for the two isolated systems. So the insistence on linearity is really just follows from my own limitations. I just don't know how to deal with isolated systems in any other context. But if someone can, well, then the kind of thing that I was doing today might be extended to that also.
I see.
Hello?
Hello, this is Jim Hartle.
Hi, Jim.
I have two questions. The first one is, usually the von Neumann entropy of the density matrix, minus trace rho, is understood as the missing information we have in a density matrix about what the state is. About what the state is, but in the way you formulate it, the missing information, as I understood it, should be zero. Do you have a different measure of missing information? That's one question. The other question is, in your book, you express the opinion that no formulation of quantum mechanics that we have today is satisfactory because it doesn't derive Born's rule. Does this help with that?
Well, those are two good questions. With regard to the first, the Lindblad equation was originally developed to deal with open systems, and in those systems you have an increase of entropy due to the fact that you're integrating out the environment. In the application of the Lindblad equation to the kind of generalization of quantum mechanics studied by Pearl and Girardi, Ramini, and Weber, they imagine it applying to a closed system, and it really represents an increase in entropy just caused by the fact that the system, well, the Lindblad equation doesn't respect time reversal invariance. The eigenvalues of the kernel are positive only for mappings into the future, not into the past. I'm not sure that's entirely responsive to your question. I mean, that's something that bothers me about this whole business, but it's not something I introduced. The whole effort to go beyond quantum mechanics by changing the time dependence of the density matrix is subject to that comment, whether it's a criticism or not, that it leads to an increasing entropy without any interaction with an external system. With regard to could you remind me about the second question?
The second question was, does this help with deriving Born's rule?
Oh, yes. Well, yes, the Lindblad equation in a very natural way produces Born's rule, and it's one of the nice things about it. And in fact, that is something I discuss in this other paper that I mentioned, which I haven't sent out yet. I'm glad you asked. But I don't think that the Born rule is getting the Born rule is the whole problem for quantum mechanics. A more general way of saying what the problem is, well, there are two problems with quantum mechanics. One is that if you take the state vector seriously as a representative of what's happening really to physical systems, then you have to be worried that you can change the state vector by measurements in a very distant system, and you can change it instantaneously. You don't have to worry about that if you take an instrumentalist point of view, that the only important thing is the predictions you make, because you can't change those predictions. You can't send a signal in ordinary quantum mechanics. But it ought to bother you that you can change, and it did bother a lot of people historically, that you can change the state vector instantaneously from a distance. And that's the reason why I want to concentrate on the density matrix. Another thing wrong with ordinary quantum mechanics, of course, is the treatment it gives of measurement. The Copenhagen interpretation is absurd, the idea that at a certain point classical mechanics takes over when you do a measurement, and the kind of collapse of the wave function is something that isn't described by quantum mechanics, it's described in some other way. I think that's unacceptable. On the other hand, if you take quantum mechanics seriously, you have in its usual description of the evolution of the state vector, then I think you can't avoid the many worlds interpretation. And I find it hard to live with that many worlds. Finally, you could take, as I said, an instrumentalist point of view, which I think is the point of view you and your colleagues take in dealing with the many worlds interpretation,
pretty much,
which is that you don't try to make a moment-to-moment description of what's really happening, but you just say what will be the results of observations. And that, I don't think there's anything wrong with that. It just doesn't satisfy a lot of people, doesn't satisfy me. I'd like to have a description, whether it's probabilistic or not, or linear or not, or deterministic or not. I'd like to have a description of what physical states are like from moment to moment.
Thank you, Steve.
Hello, Steve. This is Lenny Suskin.
Hi, Lenny. I was hoping to hear from you.
Yeah,
Good.
How are you? I'm sorry you're not here.
Me too.
Sometime in the 1980s, this Lindblad equation was actually rediscovered by myself and Banks and Peskin in a context that doesn't matter. It did have to do with black holes, but that's beside the point. What we found was that it was exceedingly difficult, if not impossible, to satisfy two criteria. One was locality and Lorentz invariance. That's one criteria. Locality and the other was energy conservation. There was no way, as far as we could tell, in a field theory to implement this without either destroying locality or destroying energy conservation. And that was the point of our paper, that you can't use this as a basic new replacement for quantum mechanics. So what do you have to say about that?
Well, I wasn't aware of that paper, and I will now go look it up.
Yeah.
There have been papers since then by the people who have been using the Lindblad equation, attempting to put it into a field theoretic context. I don't know whether there are papers on a field theoretic approach to the Lindblad equation dating from the 1990s or 2000s. But I have myself not tried.
The reason is pretty simple. As you said yourself, basically this Lindblad equation is what comes from integrating out noise.
That's one. That's one way it can come. I mean, right. That's not the way it comes in the papers.
That's fine.
That try to extend quantum mechanics.
Fine.
There, it deals with. I see what you mean. You mean the intrinsic noise and the stochastic evolution of the state vector.
Yes.
Yeah, so, that's right.
Right.
That's right.
Okay, but once you have noise in a system like that, the system is going to get heated by the noise, and energy is not going to be conserved, because you can always think about it as coming from a system which is interacting with a bath, and it can exchange energy with the bath, and in particular, the particular form of this equation will always heat the system. In other words, violate energy conservation, unless the L's, the things that you call L here, commute with a Hamiltonian. But then it's extremely difficult to keep it local. So anyway.
Yeah, well, what the L's are depends on what system you're talking about. If you're setting up a macroscopic system to make measurements, like you have physicists and apparatus in the system, then the L's are big, but you wouldn't expect I'm not sure how energy conservation would look in that system. For the microscopic systems, and that's one of the things I'm discussing in this other paper I mentioned, the L's are very small, and much smaller than the Hamiltonian. Their effect is much smaller than the effect of the Hamiltonian. And it's very hard to see the effect of these corrections. They show up as a broadening of spectral lines, I don't know that the kind of energy non-conservation.
No, I think what you're saying is if you
measure the Hamiltonian, then you measure the energy, then the Hamiltonian does commute with the L's. If you measure something else, it doesn't, and I guess you do get a non-conservation of energy, but very small and hard to detect. Maybe that's the thing to look for.
I think what you're saying is you can always make the L's small enough that you couldn't have detected anything.
Well, I think in microscopic systems they are naturally very small. Because quantum mechanics works very well. Obviously, except when you have an intrusion of macroscopic bodies like physicists, quantum mechanics works very well, so the corrections have to be very small. So on the microscopic level, the L's certainly are very small, and maybe then the tiny energy non-conservation isn't too bad.
Maybe so.
Locality would bother me more, but I haven't thought about that at all.
We should probably move on now. We're over time.
Yeah, we have to go on to Gary Strominger, and I wish I could be there to hear his talk.
Thank you again, Steve.
Can you keep the connection open so that I hear his talk?
So I'm very pleased to have our next speaker, Andy Strominger. I mentioned that I met Joe Polchinski first in Austin. Now I remember that I first met Andy at the Institute for Advanced Study when he was also a beginning postdoc. I mentioned that Joe was very good with young children, and it turns out now I remember Andy was also very good with young children. So, Andy? Oh, there's one big difference between Andy and Joe. Joe stayed in Santa Barbara and Andy left.